So in this lesson, we're looking at continuing to look at projectile motion. We're going to focus on these aerodynamic factors now. We've just remaining to look at Bernoulli and Magnus. So today we're going to focus on the Bernoulli principle, which explains the additional lift force that some projectiles can generate during flight. So we already know, we looked last lesson at the horizontal distance travelled by a projectile and what the determining factors are there. And there is a fourth factor. Obviously we looked at height of release, angle of release and speed of release. But there was a fourth factor, aerodynamics. So we're going to have a look at the Bernoulli principle today and how that can affect, how that explains the flight path of certain projectiles. So I've posted this video on the OneNote page, so if you have a watch of that video, but also what you can do, you can take maybe a piece of paper, a piece of A4 paper, if you hold it up to your mouth horizontally, so you've got the edge of the paper towards your lips, and you blow along the top of it. Have a think about what happens to the paper. The other thing that you can do is take two pieces of paper and hold them together or really close together at your lips, this time holding them vertically. And if you blow between them, think about what you would expect to happen when you blow between those pieces of paper and then what you find actually happens. And once you've done that, what you'll find is with the piece of paper, if you hold that horizontal paper in front of you and blow across the top of it, you would expect your breath to sort of blow the paper downwards, but what it actually does is lifts the paper up. And similarly, you would have maybe expected the two pieces of paper that you hold vertically in front of your mouth. When you blow between them, you would expect probably your breath to blow those pieces of paper apart, when in fact it will pull those pieces of paper together. Okay, and the Bernoulli principle is what explains what's going on there. Okay, so the Bernoulli principle explains how the additional lift force can be created during flight based on the shape of a projectile. So if you were to get asked to explain or define what Bernoulli principle is, or explain it is more likely, you would state that it's the explanation of this additional lift force. So let's have a look at a really simple example. So if we take a shape that's flat on the bottom and curved over the top, okay? What we're then going to draw in is the what's called airflow lines. So let's imagine, this object is travelling that way through the air. So it's a projectile that's travelling through the air, and this is its direction of motion. What we need to draw on are what we call airflow lines. They show the flow of air around this object. So we've got air coming towards this projectile, the projectile's coming towards the air, and this piece of air here, as it hit the bottom of this shape, it would be forced up and around, over the top of it, down and around the other side. Okay, the next piece of air here would also be forced up around the top, and by the way, those lines are I'm drawing them closer together on purpose. Again, another piece of air here, as it hits, it's forced over the top, again squeezed together. That's on purpose, that the lines are close together, and would finish over here. Whereas this piece of air here travels along the bottom and it just travels normally underneath the projectile here, and we might want to draw one more up here. So this is what's called an airflow diagram, and it's showing the flow of air around this object, around this projectile. So I've drawn these closer together because those closer lines represent high velocity air. and the wider air flow lines represent low velocity air. Okay, now we know about pressure, so high velocity air causes low pressure. So where air is travelling quickly, it creates low pressure. Where air is travelling more slowly, it creates high pressure. Now, Bernoulli found that the air splits as this air here all hits this surface of this projectile, whatever it may be. It's forced to split. But the laws of physics say that the air that splits here must rejoin here at the same point in time. So this particle of air, it splits away from this particle of air here, and it has a short journey until it gets to here where they're going to rejoin each other. Whereas this particle of air splits away from this part, and it's forced a long way around before it rejoins at this end, before they're coupled up again. Because it's got further to travel, it must travel at a higher velocity in order to get to this side at the same point in time. Similarly, this particle and this particle and this particle, they're being forced a long way around and therefore have to travel faster. So this long side compared to the short side creates these difference in air velocities and therefore difference in air pressures. Now, we know about air pressure. We know things, and that includes fluids and airs, particles of air. They travel from areas of high pressure to low pressure. So what it creates is underneath high pressure, which pushes this air wants to get up here, and it pushes this projectile. It ends up pushing this projectile upwards, okay? And it creates this lift force. Okay, now that might sound quite complicated, but if we were to describe it, we just need to talk. It's similar to like when we talked about the mechanics of breathing, okay? In order to describe this, we need to describe the shape, first of all. So it's flat on one side and curved on the other. If we had a shape that was like this, then this wouldn't happen, okay? Because this air would come and go around here at the same time that this air would come and go around here. So we wouldn't get differences in air pressures on either side. So this is happening because we've got this shape, a flat side and then a curved side, okay? So the first thing you would talk about is shape. And it's a flat and a curve, okay? The next thing we talk about is what that does to the air, all right? So it forces the air in different directions. It forces some air the long way around, okay? So it's talking about the distance, the distance that the air has to travel, and therefore the velocity of that air. So this air that's travelling over the curved side air travels a far distance and therefore needs a high velocity. The air that travels around the flat side travels a low distance comparatively and has a comparatively low velocity. We then talk about air pressure. And these are conversely related. So the large distance has low pressure and the small distance has high pressure. So we're talking about low or high pressure. We then talk about that principle of things move from the movement from low pressure, the movement from high pressure to low pressure. Which in this case then results from this low pressure area to this high pressure area, it results in this lift force. Okay, so if we had a question asking us to describe this, we would want to refer to the shape of the object, what that does to the air in terms of distance and therefore the velocity of the air travel, what that does then to the pressure of the air, talk about the fact that things move from areas of high pressure to low pressure, and that generates this additional lift force. Okay, so high fluid velocity results in low pressure and slow fluid velocity results in high pressure. This results in the creation of an additional lift force on a projectile. And similarly, you could get asked to define that lift force. So lift is an additional force created by a pressure gradient that forms on opposing surfaces of an aerofoil when it moves through fluid. And that's what this is. It's an aerofoil, flat on one side and curved on the other, which forces the air to split, forces the air to travel at different velocities on either side of it, and therefore creates areas of high and low pressure, and therefore this additional lift force. So the airfoil shape takes more layers of the air the long way around, so this air must travel further and therefore higher velocities. And you can see again on this diagram, the airflow lines are close together, and that is depicting, showing the fact that we've got high velocity air. We're going to talk about angle of attack in a little moment. So we've got the curved top, it's further distance, faster airflow, low pressure, flat bottom, small distance, slow airflow, high pressure. We've got this pressure gradient formed. As all fluids move from an area of high to low pressure, it creates this additional lift force. So what in terms of sports? So the advantage then is when we are in sporting contexts where we're trying to achieve the maximum horizontal distance, if we can achieve this additional lift force, it's going to make this projectile hang in the air for longer and therefore extend its flight path and its horizontal distance travelled. So we're going to try to generate this additional lift force using the Bernoulli principle in any sporting context really where we're trying to achieve maximum horizontal distance. So the three that appear on the specification are ski jumping, discus and javelin. So let's have a look at ski jumping first of all. So we've got our ski jumper, and effectively what this ski jumper is doing with their skis and the shape of the body is creating an aerofoil. So we've got the bottom of this object and a curved top. Now obviously there will be some air passing through, but essentially this is our direction of motion. And you could get asked to draw an airflow diagram for a ski jumper. So we've got air coming this way and straight under the skis, nice and quickly. So it will be travelling flat, and then it's going to be forced down around this ski before it continues on. This piece of air, to be fair, might just travel through. It might be lost, it doesn't help in the effect. But what you see with the ski jumper is they've got this the helmet, and the way the ski jumper holds their head, really, and we probably should have drawn on their body, is that as this piece of air hits their helmet here, it gets forced around this curved top before it meets the air again at the bottom. This piece of air gets forced around this curved top before it comes back to normal at the end. This piece of air gets quickly forced down here. Okay, so what we end up with a ski jumper is high velocity air, and low velocity air, we're going to say this equals low pressure, this equals high pressure, then we would say all fluids move from an area of high to low pressure, and therefore it's going to create this additional, it's going to create this lift force here, and it's going to create lift. So in the end, we've created lift force. Okay. Let's have a look at the discus. So again, we've got the discus travelling through the air. I'm going to draw this going the other way because sometimes in the exam actually they do this to try and confuse you. So because we often draw for some reason direction of motion this way. So let's draw direction of motion this time this way. Just so we're used to not always assuming we're going left to right. So the discus would be therefore travelling at this sort of an angle, and the thrower releases it at that angle. I'm going to look at the angle of attack later. The thrower releases it at that angle on purpose. So we've got some air hitting the discus here, and it would travel down and then off this piece of air, whereas this piece of air here would hit the discus and it would be forced all the way up, around and down. Okay, a much larger distance than this piece of air. Again, this piece of air would be forced up around. I'm drawing the lines closer in order to represent higher velocity air. Here, close lines to represent high velocity, back to normal. Okay, so again, we've got high velocity air, which equals low pressure. We've got low velocity air, which equals high pressure. Things move, or all fluids move from high to low pressure, and that generates the lift force. So we've got the air here that wants to get up there because this is low pressure, this is high pressure, and it ends up generating the lift force. Finally, let's have a go at drawing a javelin. So this time we're going to have the direction of motion going this way. We're going to draw our javelin like this. Now the javelin is very, the javelin is very thin, isn't it? Okay, so again we've got air hitting here, would be forced down and off. Air hitting here, forced down and off. But the air that hit here gets forced all the way up around the javelin and down and off at the other side. All the way up, high velocity tight, and then back to normal over here. High velocity here, low velocity. So yet again, we've got high velocity air, which equals low pressure. Low velocity air, which equals high pressure. All fluids move from an area of low pressure to high pressure, and that gives us lift force. We've got this air here that wants to get up here, and it pushes the javelin upwards. So, I mean, there's an optimum angle of attack for this, for each sporting activity. So, for a javelin, the optimal angle of attack is 5 degrees. Now, this is different from the release angle. We know, let's have a look, the release angle of a javelin, because it's got a positive release height, the optimum release angle of the javelin is somewhere between 35 and 40 degrees. That's the angle of release. The difference between the angle of release and the angle of attack is the difference between what's called the angle velocity vector, which is the flight path of the centre of mass. So this diagram shows the flight path of the centre of mass, okay? And then the difference between that and the angle of what's called attitude, the orientation of the javelin. Now, you don't need to know any of those words apart from just trying to help you understand what we mean by angle of attack. So this is the line that the centre of mass would travel. And now, if the javelin's thrown like this has a big angle of attack, or what's referred to as the angle of attack. Whereas on this one, this is the centre of mass, and this has a small angle of attack. Now, for a javelin, we were looking for a small angle of attack. We've got a positive release height, and the thickness of the javelin is very small, and so it has a very small optimal angle of attack. So for javelin, yes, we want to release the javelin between 35 and 40 degrees because we've got a positive release height, but then the way the javelin is angled as it goes through the air wants to be at 5 degrees. Okay, the difference between where its centre of mass would be and where it is pointing, this area that's shaded in yellow here. Okay, for a discus, it's bigger than that. The angle of attack is greater. It's more like 17 degrees is the optimal angle of attack, and obviously they've used wind tunnels in order to measure this. So they would have used wind tunnels where you can see the airflow to measure exactly what's the best angle of attack for the discus and what's the best angle of attack for the javelin. And they would be able to see that using wind tunnels. Actually, in the wind tunnel, the javelin itself or the discus itself is still, and they blow air at the object. And using the technology of the wind tunnel, they can see where that air is going and then calculate this optimal angle of attack. So for a discus, it's 17 degrees. The discus is not as long and it's wider than a javelin, which explains the difference. And then we've got our ski jumper, which has quite a wide ranging angle of attack, somewhere between 25 and 40 degrees. Now, this is a lot bigger. The ski jumper has other factors to think about. Okay, there are more variables, such as this. The V angle is how they hold their skis. They also have this ankle angle here, and so there are lots of variables with a ski jumper. Some ski jumpers use a wider V angle, and that's going to affect the aerodynamics. Some ski jumpers use a smaller or a bigger angle at the ankle, and that affects the aerodynamics. Whereas obviously a discus and a javelin, they are what they are. They don't change, and so we can say with a great deal of certainty what the ideal angle of attack is, whereas with a ski jumper we've got much bigger variables. So somewhere between 25 and 40 degrees is the optimal angle of attack for a ski jumper. Now then, all that you need to know in terms of the exam is what the optimal degrees are, and potentially an explanation of why they are different. Okay, so here we've got a different shape, we've got a smaller degree, we've got a much thinner, longer object, whereas here we've got a much shorter but a fatter, wider, a deeper object which explains the difference. And here we've got a large window due to the fact that there are much more variables in flight acting on the ski jumper. Okay, so this is just an idea about the fact that we've still got our angle of release and then our angle of attack. Okay, so they were our airflow diagrams, and we can use an airflow diagram like this to explain the Bernoulli principle, to explain that through a diagram, to say that you know, air is being forced either under or over an object, either over the top of and underneath an aerofoil shape, or underneath and over the top of an object that's released at a certain angle of attack. Obviously, a discus and a javelin, they aren't aerofoil shapes, but because we're releasing them with this angle of attack, then we achieve that same effect. We achieve air going over the top and air coming underneath. We can now use free body diagrams, resultant force diagrams, and then flight path diagrams to actually show what that results in. So free body diagram is going to show us the forces acting on the projectile while it's in flight, and then the resultant force diagrams and the flight path diagrams show us are there to sort of indicate what that actually means for the object in flight. So first of all, let's think about a free body diagram, and let's go with the discus again. So we'll draw the discus travelling left to right this time. So don't forget your direction of motion on these free body diagrams. So this is free body diagram, sorry, to start off with. So obviously we've got weight acting, and we have air resistance acting. Now I would have drawn weight as the dominant force here because obviously a discus is quite heavy in comparison to air resistance. It's quite low on it. It's quite it's got a reasonably small frontal cross-sectional area. It's got a smooth surface, but it is travelling at high velocities. But I would have said that air resistance has the weight is the most dominant force until, and now I'm going to draw on this additional lift force. Okay. So this is my free body diagram now for a discus. So I've got weight, which is bigger than air resistance, but I've also got lift. Okay. So that's a free body diagram. Now I'm going to draw a resultant force diagram. Now, with the resultant force diagram, sorry, I probably shouldn't have done that. Let's draw it next to it. Resultant force diagram. I'm going to draw in the centre of mass and the air resistance exactly the same. But now what I do is actually what we call resolve these forces. I'm going to take lift away from weight because this amount of lift is cancelling off weight. So this amount of lift here is going to reduce weight by the same amount. So I'm only going to be left with this much effect of weight. Okay, so now I'm going to draw on weight, but I'm drawing it only this big. It effectively is the original weight minus lift force. Okay, so free body diagram doesn't, the resultant force diagram doesn't contain, you don't show the lift, but what you've done is minus lift away from weight. So then I'm going to draw on that parallelogram, and therefore the resultant force and what I've got here now is the resultant force closer to air resistance than weight. Now if we hadn't managed to achieve lift because we've got the angle of attack wrong, then obviously we'd have had a diagram that looked like this, and the resultant force would have been, wouldn't it, over here. You must make sure you're drawing those dotted lines, don't be lazy. So we've got our resultant force closer to weight, which would have been dragging this discus down. But if we can get it right, if we can generate this additional lift that's going to cancel off that amount of weight, and it's giving us a resultant force that's nearer to air resistance. So the last thing that we can draw on is a flight path diagram. So because we've got our resultant force closer to air resistance now, we have a non-parabolic flight path where the discus is going to go up, reach its peak, and then hang in the air. Okay, so if we look at this from its top, from its maximum vertical distance, it's not symmetrical. Okay, we've obviously got a positive release height for a discus. It's not symmetrical, it's asymmetrical, and this line it's hanging in the air. Okay, and I would label that. So it's non-symmetrical, it's non-parabolic, and we've got the discus hanging in the air. And effectively that maximises the horizontal distance travelled. So a discus thrower would absolutely be trying to get this angle of attack correct at that magic 17 degrees, because if they can generate this additional lift force, it reduces the effect of weight on the discus. It brings our resultant force closer to air resistance, producing a non-parabolic flight path, allowing the discus to hang in the air, maximising the horizontal distance travelled. So that's been about technique, really, how we can use the Bernoulli principle to alter our technique. So in throwing events or in that ski jump, to maximise the angle of attack in order to generate that Bernoulli, the additional force of lift, and also with the ski jumper taking on that aerofoil shape in order to maximise that additional lift force. But we can also think about the design of equipment in sport and how we can use the Bernoulli principle to help us design equipment. Now, often this is actually in reverse. So we see our aerofoil that we've already drawn. The direction of motion, by the way, which isn't shown on these, is this way, isn't it? Direction of motion. The air's hitting the front of the aerofoil here. It's being forced over the top. So this is what we've looked at. This is what we've looked at already. We can invert that aerofoil, turn it upside down. Okay. So in this instance, then we've got the flat bit at the top and the curved bit at the bottom, and that means that the air over the top is travelling slower and has higher pressure, and the air travelling underneath is faster and has lower pressure. All fluids move from an area of high pressure to low pressure. So in this case, we've got this happening, and it's pushing downwards on the aerofoil. Now, confusingly, this is called downward lift. Downward lift force, still called lift, because it's this additional force that's generated due to the shape of the object, but it's forcing the object now downwards rather than upwards. So in cycling we see this. The helmet shape forces air down and under. So if we were to draw our airflow on here, we would have the air particles here would travel over the top, over this flat area, but the next bit here would hit the helmet, would be forced all the way down, round and through the cyclist here, the long way around. Bit of air here would travel at high velocities, so I'm drawing the lines nice and close together. And again here would hit and be forced down this way. Some air might even be forced all the way down under the bike. Okay, so here then we have low velocity, high pressure, we've got high velocity, low pressure, we've got, it's creating this pushing down on the cyclist, which is going to generate this downward lift force. And that holds the bike to the surface. So track cyclists are really looking to create this downward lift force, and they do it by having the seat high, which creates a flat back. If they had the seat in a low down position, then their back would be sort of be at this sort of an angle, which would force the air a long way around. So instead they've got a flat back by having a high seat, and also the shape of the helmet creates this flat top of the cyclist and then rounded underneath of the cyclist. And it's creating this additional downward lift force, which helps the cyclist stick to the surface, to the velodrome surface, and it means that they can attack the corners at high velocities without skidding outwards. So we've got this downward lift force created through the use of an inverted aerofoil or an upside down aerofoil. It's also used in Formula 1, okay, and it's the same principle. Formula 1 track cycling helps to hold the core of the bike to the surface, enabling high velocities around corners. So let's have a look at a Formula 1 car. So the spoiler, that's the bit at the back here, that's designed as an inverted aerofoil. So it's got a flat top and a curved bottom inside here, and it forces air as it comes over the top of the car. It forces this air down and around, as opposed to forcing forcing it. This bit would just go over the top. So it's creating a pressure gradient here, which creates this downward lift force because we've got higher velocity air down here and lower velocity air down up here. High pressure up here, low pressure down here, creating downward lift force. Also, what we've got on a Formula 1 car is the front wing, which is here. Okay, now if we were to look at the front wing from front on, it would look something like this. Okay, so there are funnels. Now this bit is infilled, so the air would just hit this surface, and it then gets forced through these much smaller funnels. Okay, now it's the same principle. This is extra, you don't need to know this, but this is the Venturi effect, who followed on from Bernoulli. It's the same principle, but rather than using this aerofoil shape of a flat top and a curved bottom, it uses this principle that if you force the air through funnels, then it has to travel quicker. So again, we've got air hitting the front of the spoiler, or the front wing, sorry, and some of it just travels like over and through a gap, but the bit that's traveling here is forced through these funnels, and it travels very quickly as it passes through the front wing. So it's not really to do with shape, it's to do with the funnels at the front end of a Formula 1 car. But it's the same principle. It's fast, it's then high velocity because it's being forced through a small space, compared to low velocity over the top of it. And again, it creates this downward lift force. So with a Formula 1 car, we've got downward lift coming from the back spoiler. We've got downward lift coming from the front wing, and that effectively sticks the car to the ground and allows it to travel around corners really quickly. And that's why they say, you know, a Formula One car could stick to the roof of a tunnel, and they've done it in some films, haven't they? I'm not sure they've done it for real, but where you see a Formula One car travelling at really high velocities sticking to the roof of a tunnel. It's in that James Bond, isn't it? But it's because if we turn this on its head, then we would have lift force, traditional lift force, rather than downward lift force occurring on the Formula One car. Now, this is actually a past exam question. So this was the recognised mark scheme for this. So state Bernoulli's principle and apply it to the design of a Formula One car. It was 5 marks. So obviously state the Bernoulli principle is an AO1 mark. Application of that knowledge, AO2 mark, 4 marks available. So state the Bernoulli principle. The higher the velocity of airflow, the lower the surrounding pressure. Gases move from area of high pressure to low pressure, which creates this pressure gradient and therefore lift force. So in terms of the 4 possible applications, so in the spoiler we have an inverted or reverse aerofoil. The angle of the spoiler creates a downward force, and interestingly it's actually 17 degrees, so it's the same angle of attack as the discus but upside down. So it's force in the air the other way around. Air travels further and at a higher velocity under the spoiler than it does over the top of the spoiler, which creates pressure lower under the spoiler and high pressure over the spoiler. Air travels, which causes pressure to be higher above the spoiler, and therefore obviously creating that downward lift force. And then we've got this point about the front wing. The front wing diverts air further or through a smaller space underneath the chassis of the car, which increases the velocity of the air and decreases its pressure. And the overall effect then is to enable the car to be able to hold on to the road around a bend at a higher speed. So we've got that idea about that's the spoiler. So we said shape of the object is the first point to make. So inverted aerofoil, flat on the top, curved underneath. What does that do to the air? It causes the air to travel a further distance and therefore at a higher velocity. What does that do to the pressure of the air? It means that the pressure under the spoiler is low. It means that the pressure above the spoiler is high. And that means that we get a pressure gradient and therefore that downward lift force being generated. Okay, so that's everything on the Bernoulli principle. Key things here then to really take away from this lesson are the idea of an airflow diagram, and that we use close together arrows to show high velocity, or lines, and far apart lines to show low velocity. Where the air has to travel further, it's going to travel at a higher velocity to meet that same particle of air at the other side. That creates a pressure gradient, further distance, fast air, low pressure, shorter distance, slow air, high pressure. Pressure gradients formed. All fluids move from an area of high to low pressure. It creates the lift force. Then we looked at how that specifically is going to affect a ski jumper, a discus thrower and a javelin thrower by drawing airflow diagrams, and then looking at the specific angles of attack. 5 degrees for the javelin, 17 degrees for the discus, somewhere between 25 and 40 degrees for the ski jumper, depending on what they're doing with the skis, with the ankle. There's more variables there, and so there is a larger window. Remembering that the angle attack is different to the angle of release. We've still got that optimum, something like 35-40 degree angle of release for a discus and a javelin because of that positive release height. But now we've got the angle of attack, the sort of difference between where the centre of mass of the object would go and how the object is orientated. And finally, we've got our free body diagrams, resultant force diagrams, and then flight path diagrams for these projectiles. So free body diagrams, we would show the lift force. Resultant force diagrams, we take lift away from weight, which just gives us air resistance and weight. We draw our parallelogram of forces and therefore our resultant force. And by taking lift away from weight, we have a resultant force close to air resistance, giving us a non-parabolic flight path and that discus hanging in the air. Same for javelin, same for ski jumper. Okay, and then we've got this idea of downward lift. If we invert the aerofoil, we're forcing air in the opposite direction. This time, the fluids would want to move from the top of the aerofoil downwards, which pushes the aerofoil down, and we see it specifically in sports, high velocities where they want to stick to the ground, such as track cycling and Formula 1 racing.